Hello, everyone. Today, we're going to talk about the paper, Self-Organizing Network Modeling of 3D Objects. My name is Hui Yang, and this is a joint work with my PhD student, Runsang and my colleague, Dr. Soundar Kumara. We are from the Department of Industrial and Manufacturing Engineering at Penn State. So before we get started, let's have a look at advanced manufacturing. For example, the additive manufacturing. Additive manufacturing produces the parts, complex designed parts, like layer by layer. This gives us a lot of design freedoms, okay? And you can imagine that a person can sit at home and receive the design and print the parts with a 3D printer and then ship to the customer. So the manufacturing is transformed from a centralized fashion to a more distributed manufacturing. And the speed is much faster than before. And we can print directly from the digital design, for example, the CAD model, and with materials and simplified processing steps, just layer by layer. However, not everybody is an engineering designer. So, but if we look at the website, we can see that a lot of designs are readily available from the past. Not only the designs, but also the processing plans with different kinds of machines. So can we reuse all the knowledge we accumulated in the past, or we reinvent the wheel every time? And this is a website called 3D Warehouse. And you can search the design, but you can search the design based on the keywords. However, the keywords is a very simple text description of the design. It cannot give you all the detailed features of such a design. So is it possible that we can upload a design and then retrieve all the similar designs from the database? So in order to do that, we need a 3D representation. So these are the different kinds of 3D representation. You can have a polygon mesh, and you can discretize them into voxels. And all you can use the spherical harmonics decomposition to decompose the 3D objects into different frequency and then calculate the spectrum in a particular frequency band. And then you can compare, right? So those are the different kind of 3D representations. So, but there are some practical issues with the traditional approach. For example, the spherical harmonics decomposition. So we have a 3D design like an L plane right here, and we can discretize and become voxels. And then the traditional SHD, spherical harmonics decomposition, they use concentric circles or the balls, and they try to use different radius and then check the intersections and then calculate the harmonics. You see the origin of the center or the mass center of the L plane can be different. If it shifts a little bit, and the intersections between the ball and the L plane will be different. And also, even if you have a slight angle shift or rotation shift, there will be some difference. Okay. And then based on the different size of the different radius of the balls, and you can get the intersections and then do the spherical harmonics decomposition. And then in each frequency band, you see each frequency band, you can do the L2 norm of those spherical harmonics component and different radius. For each radius, you can do that, okay? And then you get a descriptor of the 3D objects, and then you can compare the similarity between the designs. As I said, the practical issues can happen in each step. The discretization step, where do you place the L plane, or the rotation shift, or the L plane, the angle can be rotated a little bit, or there's a slight difference in the wings, and there will be some big difference in the representation. So, so instead of the spherical harmonics, we had a new idea to use the network representation. So what is the advantage of network representation? So we can discretize and then become voxels. Okay, we can treat each voxel as a node, and then node, and they have relationships. For example, each node, they might have neighboring nodes. So what the network actually not only treat each voxel as a node, but also preserves the node-to-node relationship. That means the structured relationship of the chair, they are preserved in the network. So this is an adjacency matrix. We couldn't see this is a chair, and but we can use a network. We can put it in a network. Okay, so this is called a network representation. And network representation is widely used in different areas. For example, social network. We can check each person have how many contacts, social contacts. And also the molecular biology, for example, a virus and all the proteins, they are interacting with each other. So we can study this kind of interactions and then discover the cues or the drugs. And for the different kind of virus, for example, the infectious disease, COVID-19, you study all this kind of relationship of the virus structures and all the computer networks. So in network representation, we use the adjacency matrix A to represent how nodes they are connected to each other in the network. Okay, if two nodes, for example, node I and J are linked, then we adjacency matrix the corresponding location matrix element Aij will be 1 or 0 if they are not linked. And after you build the network, you can have you can extract or characterize the network statistics, and from the network, which is also called statistic quantification of the characteristics of the network. And those statistics will give you some characteristic features or salient features about the network. There are different ways to construct the network. The first one is called, I will give you a few examples here. The first one is called K nearest neighbor network, which is a direct network. Each node is connected to K nearest nodes in the network. That means we are trying to fix the number of neighbors, okay? Each node have a fixed number of K neighbors. And the second one is called a recurrence network. So this is also a undirect network. Each node may have a different number of links in the network. That means we're going to fix the neighborhood, the size, for example, the radius of the neighborhood for each node or each voxel. Then we check how many voxels they are close to this voxel, okay, in the radius of the ball. And there are also some other approaches like transition networks, cycle networks, correlation networks, visibility networks. And in our group, we and my colleague, Dr. Kumara, and our PhD students, we showed that recurrence networks yield a very good framework to transform either the one-dimensional time series, nonlinear time series, or the two-dimensional spatial data, that means image data, into complex networks. So in this paper, we are studying the three-dimensional data. That means the complex design. We want to see how the networks can effectively capture the characteristics of the 3D objects. So now let's have a look at, dive into a little bit details on how to construct the networks. For example, here, this is an illustration, a node in KNN network. A node Xi is connected to its K nearest neighbors. That means for a node I, if we have K nearest neighbors and J belongs to the K nearest neighbors, then we are going to mark as a 1. Otherwise, it's a 0 in the adjacency matrix. For example, here, this is a node. Then we're going to find where are the K nearest neighbors. Then we're going to connect them. And then we shift to the next node. We are trying to find the K nearest neighbors. We have to find K neighbors, okay? We're not fixing the neighborhood size or the radius. Then this will be the KNN network we constructed from this cloud of dots or the voxels. On the other hand, we have recurrence network. The recurrences are treated as links in the network, okay? And we are going to use how close they are. This is called a recurrence in the space. And we are going to use the recurrence matrix minus the diagonal identities. So Iij minus Iij. So why we minus the diagonal identities is because we don't want self loops, okay? So for example, for this node, we fix the radius and we find how many labels it has, okay? And also for a different node, we fix the neighbors. That means each node might have a different number of neighbors, and it might have different number of connected nodes, okay? And this is a recurrence network we constructed from the same group of points in the space, just as the previous one. You see the structure will be a little bit different. However, the question right now is, if we use KNN or recurrence network, which one will give you a better representation of the 3D design? So this is a technical question we want to address. And I'm going to show you the experiments later, which one is better, okay? And once you construct the network, you can extract the network theoretical measures like a node degree, link density, distance, average path length, diameters, and clustering coefficients. Those are just some example measures. You can extract more measures from the network. And in the network theory literature, there are many measures you can do. But those are some classical measures, and I want to show you how it works. So the node degree, for example, node degree Ki, that means how many neighboring nodes node I has. So this is actually, for the Ki, is actually a row, for example, Aij. You see, for a row I, you just count all the j, you find how many of them are non-zeros. That means you count how many ones in a row in the adjacency matrix. And the link density is, you just count how many non-zeros in the adjacency matrix and divided by the number of total possible edges. That means the ratio of the number of edges to the number of possible edges. So the distance. So distance is the minimum number of edges to travel from node I to node J. As you may know, there are digesterone algorithms that can help you to calculate the shortest distance from a node I to node J if there is a connected edges. So average path length is the average of all the paired distances between the nodes, okay? So diameter is the longest of all shortest paths. That means you have Dij is the shortest path, and then you're trying to find the longest of the shortest path, okay? The clustering coefficient of a node, this is the probability that two neighbors of a node I are also neighbors, okay? And you may note that most of the metrics, they can be calculated from the adjacency matrix. So once you have the adjacency matrix, you can get those measures, okay? So this is an example how to calculate the theoretical network measures. For example, the distance between node A and B is 6. For example, node A and B is here, so you can count how many edges you pass through to reach B. So this is the shortest path. You can use the digesterone algorithm to find that. And the average path length, you just count the node distance of all of them in the network, and then you do the average. The clustering coefficients, this is a node degree. For each node, you count how many of them are connected to this node. This is, here we have about 30 nodes. So for each node, we're trying to check how many of them are connected to this node. The clustering coefficient is, for example, for node 1, it's 94.48. This is very big. And however, for node 20 is 0. And 100%, everybody is connected to node 27. And the averaging clustering coefficient for the network is 62.71%. But those network theoretical measures, we just count, okay, how many we have between these two nodes. We didn't actually use the node-to-node distance, because if the network topology is different, then even you have two nodes, they're connected, they might in different distance, right? So the question is, if you have an adjacency matrix, how do you derive the topology? If it is a good adjacency matrix of the 3D objects, so how to derive the network topology from the adjacency matrix? And what will it be? I mean, what is the network topology will be, right? This is an interesting question. The first interesting question is, KNN and recurrence network are different kinds of network construction methods. Which one is more effective for to represent the 3D objects. And the second one is, once you represent, you got the adjacency matrix. How do you get the network topology from the adjacency matrix? So you see here, we have a adjacency matrix, and we might have different possible topology structures from the network. So for example, for this adjacency matrix, you see those ones only define which node is connect to which one. For example, 4 and 8, they can be connected. However, 4 and 8 can be connecting this way or this way. The network can take different form, even if you define the connections between them, right? So if we define or represent the recurrence network from the 3D objects, is there a unique or stable topological structure we can derive from the network? Okay. And then we propose to use self-organizing network. So we treat each node as a electrically charged particles, and the edges are springs between the nodes. Then we define the repulsive force exists between any pair of nodes, because these are particles, right? Particles, if there are repulsive force among them, so that means every one of them, if they get closer, they're going to have repulsive force. But the attractive force only exists between two neighboring nodes. That means if you have a spring, connect the two nodes. If you drag it further away, the spring will pull them back. This is called attractive force. The repulsive force, you see here, this is a repulsive force, and this is a distance between two nodes. Okay, and this is inversely proportional to the distance. Okay, that means if the distance is closer, that means the repulsive force is stronger. However, here, if the distance is longer, then you have a spring between two nodes. However, if you pull these two nodes further away, the spring will pull them back. The further it is, and the stronger the attractive force. Okay, and then we are going to calculate the combined force at a node I. For example, here, this is I doesn't equal to J. That means for any pairs, we are going to have the repulsive force. But here, this is only connected between I and J. So that means attractive force, we only count those who are connected. And here, you see this is P plus 1, this is P. Why? Because we are trying to define the directions of the force based on, because here is normed. And here, this one actually define the directions. And this one, we take one out, also define the attractive force direction for each node. Then you sum them together, you will be able to calculate the combined force at a particular node I. And then what we are trying to do is, you have combined force in each node I, and then we're going to take the square, and then we are going to count all the nodes. Okay, we sum them up. This is called energy of the network. We're going to minimize this energy. So as the energy is minimized and reaches a stable phase, we're going to have a stable topology of the network. Okay. So this is a fundamental idea behind the self-organizing network. So let's have a look at an example, okay? Here we have an adjacency matrix. Now we start from two different layouts, okay? Two different layouts. That means the nodes, although the adjacency matrix are same, we're going to randomly put the nodes at different locations, but keep the connections the same. And as we are deriving the force, minimizing the energy, and the network topology is going to show up, right? You see here, this is about 350 iterations. So 350 iterations, the energy is not stable yet. But once reach 2,000, maybe 3,000, it will get stable. So now we are at about 2,000. So after 2,000, we will be able to see, okay, the shape of the network. You see here, this unique adjacency matrix actually define a unique topology. So the self-organizing approach actually gives you a unique and stable network structure by minimizing the system energy, even from different initial settings. Okay, this is a very interesting finding, okay, from the study. Now, We talked about the KNN and the recurrence. Now let's self-organize for the same. This is a chair. This is a chair. We derive the adjacency matrix from the chair, and then we put different initial settings of the nodes, and then we let them self-organize. We use KNN to derive the adjacency matrix. We also use recurrence network to derive the adjacency matrix, and then they will self-organize. You see, recurrence network once converge, we can get the chair. You see, interestingly, we get the chair back. That means the adjacency matrix is the network is actually a very effective representation of the chair, and because you can get the chair back, and it's actually captures all the characteristics of a chair and how they are connected, all the voxels. And you can also change different settings. You can put the nodes at different locations. As long as you define the connections, eventually they will become a chair. Okay, so this is an interesting finding, because as long as you define the connections, even if you shift it a little bit, rotate it a little bit, it doesn't change anything. Eventually, it will become the chair. So these experiments actually show us the recurrence network actually is a better way to define the to derive the network representation of the 3D data, three-dimensional data. Now here is an animation of the chair, and we derive the adjacency matrix from the chair, okay? And then we self-organize by minimizing the energy. And a few iterations later, we will give you back the chair, as no matter how you randomly place the nodes, okay? So we have a YouTube link over here. If you are interested, you can click the YouTube link and look into the video. And this parameter setting, P equals to 5, and the granularity is 64. Okay. 64 means the 64 by 64 by 64, we're going to define the voxel matrix. Okay, I missed the end. You see, this is animation. We can not only just do it for the chair, and by the same parameter settings, you can see that we can also do it for the 3D design of the end. So this actually gives us a lot of implications. That means if you have the network representation, actually, you can, based on the network, you can search the database for a similar network. And you can also search a sub-community of the network, okay, using the network representation. Because the network is an effective representation, you will be able to search not only the entire network similarity, but also the sub-network similarity. That means not only the whole design, but also part of the design, you can actually get it. And this is an object of the drone. And so you can see we do it for different kind of objects, the chair and the ant and the drone, and we also tried different kind of designs. And the network representation amazingly works. Okay. So now let me conclude this paper. Interestingly, self-organizing network recovers the geometry of 3D designs. And this shows this is a very effective representation, and also provide a new way for optimal matching and retrieval of engineering designs, not only the entire design, but a portion of the design. And in our future studies, we're going to study that. So the important factors impact, of course, there are parameters in between in the process, okay? So network construction method, we showed that recurrence network is much better than the KNN network. And the parameters, we test different kind of parameters. If you look into the paper, we test a range of parameters P for model parameter P. If it's too small, then it will tend to tightly cluster. Otherwise, they are loosely distributed. That means the force is not controlled very well. And the granularity, of course, if you increase the granularity, a network representation actually become finer and finer, and they capture finer details of the object. But the computation is going to be more expensive, because there will be more voxels Okay. So those are the relevant publications. If you are interested further details, you can check our previous papers on chaos and operation research, annals of operations research, and also the previous CIRP conference. Okay, so this is the end of my talk, and I will be happy to answer any question of you. And if you have any questions, please feel free to shoot me an email. Thank you.